So welcome to the 36th lecture. Again, reference is Jeff Erickson. In fact, most of the remainder of the lectures, so this week and next week, it's going to be Jeff Erickson's book. Maybe I might refer to CRRS a bit, but most of it will be from Jeff Erickson's. So last week, we were looking at Dijkstra's algorithm. We were proving the correctness of the algorithm. So only improvisation or specialization of force algorithm that Dijkstra did is he used a priority queue, okay, and applied the relaxed step or checking for tenseness is based on the elements extracted from the queue. Okay, so all outgoing edges of a vertex extracted from the queue. By the way, one just note. So this is pronounced as Dijkstra. Okay, so this is ij is pronounced as y. Okay, so many people would tend to pronounce it as Dijkstra, which is not. Okay, it's ij is y. Okay. So this was an example. Last lecture we proved the correctness part of it. So one thing is for Dijkstra's to work correctly, the graph should not have negative edges. Okay, so what we saw was if the graph has no negative weights, then if you look at the order in which vertices are extracted from the queue, then the distance from the source vertex to that vertex keeps on increasing. Okay, and so using that, we can prove that every vertex will be extracted from the queue at most once, and hence it will be inserted into the queue at most once. Okay, so that basically gives us the running time bound. So overall complexity, so there will be n insertions and as many as extract min operations. The decrease key operation can be caused by an edge at most one, so there will be edge many decrease key operations. So overall complexity will be order of m plus n log n. If you use regular heap, you can improve it to Fibonacci heap, improve it using Fibonacci heaps, but the bound will be amortized to n log n plus m, okay, up to a constant factor. Now, for correctness, so we need to argue that the distance and the predecessor relationships are computed correctly. That is, if you trace back the predecessor relationship, it should give an s to that vertex shortest path. Okay, and the distance should be the correct shortest path. Here is a statement, so which we try to prove in the towards the end of the last lecture. I'll just go over it in full detail today. Okay. So suppose G has no negative weight edges. The whole of last slide, I mean, I had mistakenly written this as cycles, I think, everywhere. So I corrected it now. Suppose G has no negative weight edges, then after the termination of Dijkstra's algorithm, distance V is the length of a shortest S to V path. And if you look at this path, V, the previous vertex is predecessor of V, and then predecessor of V, and so on. And you get S is such a shortest path. So we'll prove the first part, and then we'll see that the second part immediately follows from the proof. Okay, so the same argument, if you apply with this specific path, you'll get that the value, that is weight of the path, matches with that of the shortest path. So the argument is fairly simple. We look at an arbitrary path, S to V. So fix any vertex V. So this argument is with respect to an arbitrary vertex V. So for every vertex V, the statement must hold. You fix a path, let's call it as a rho, which is starting at S. I will call it as V0 and ending at V. We call it as Vk, k greater than or equal to 1. Okay. Now we argue that weight of rho is at most distance V. Okay, that is sum of weights in the edges, sum of weights of the edges in the path is bounded by the distance V. So hence for every S to V path, distance V is at most length of that path or weight of that path. Okay, So in other words, if you take the shortest one, distance will be equal to that of the shortest path. Okay. So the argument is via induction. What we do is we take prefixes of the path, or we chop the path at length I. Okay. So rho I is the path starting at S, which is V0, and stopping at Vi. Okay. So let's say Li is the weight of this path. So what you do is you look at this path, say, sorry, S is V0, V1, V2, etc., Vk, which is V. Okay, so you stop the path at ith location. Okay, so call this as rho I. Now by induction, we'll argue that distance of Vi at most Li. Okay, so when we instantiate I equal to k, we get what we wanted to prove. Okay, so that in turn proves the theorem, at least part one of the theorem. Okay. Okay. So let's go over the proof. It's fairly straightforward, not much non-trivial, but I had rushed through it in the last lecture, so I just want to go over it again. Okay, so the base case is I equal to 0, nothing much to, because V0 is S. Okay, so for any I greater than 0, so what we have is, by induction hypothesis, distance of Vi minus 1 is at most Li minus 1. Remember that Li minus 1 is the length of rho I minus 1, that is path from V0 to Vi minus 1. Okay, or as we call it as prefix of the path. Okay, we just look at path as a sequence, then prefix is well defined. Okay, now so let's just imagine the algorithm immediately after Vi1 was extracted and before you do any further extract min operation. Okay, so you look at Dijkstra's algorithm when Vi minus 1 was extracted. Okay, so the extracted element here is Vi minus 1. Okay, so what does it do? As soon as it extracts Vi minus 1, so it does this relax operation for all outgoing edges of Vi minus 1. Okay, now so in this path that we have taken, so we have an edge from Vi minus 1 to Vi, right? So this is, say, Vi minus 1, this is Vi, let's say. Okay, so there is an edge. So in other words, Dijkstra's algorithm will see if Vi minus 1 Vi is tense. If so, it will apply relax. Okay, so now we'll just look at the scenarios, whether this relaxation step happened or not. Okay, so let's look at the possibilities. Yeah, so immediately after Vi minus 1 is extracted from the queue, so there are two possibilities. Either the distance value, that is the value stored by the algorithm, yeah, is at most distance of Vi minus 1 plus weight of the edge Vi minus 1 Vi, or there was a relaxation step immediately after Vi minus 1 is extracted. Distance Vi will be set to distance Vi minus 1 plus weight of Vi minus 1 comma Vi. So in either case, what we have is distance of Vi is at most distance of Vi minus 1 plus weight of the edge from Vi minus 1 to Vi. Okay. Now by induction hypothesis, this value is at most Li minus 1. So this is at most Li minus 1 plus weight of Vi minus 1 to Vi, which is nothing but Li, right? So what is Li? So Li is weight of Li minus 1 plus the edge, cost of weight or weight of edge Vi minus 1 to Vi. Okay, so in other words, this is at most Vi. So yeah, this should be Vi, sorry. So distance of Vi is at most Li. Now, so yeah, so that is what we require, right? Distance of Vi is Li. So therefore, distance of Vk is at most Lk. That is, distance of V is at most weight of rho. Okay, so that is what we have achieved. So what does it prove? So for any S to V path, the distance value stored by the algorithm at the end of the algorithm is at most length of that path or weight of that path. Now you take the shortest path, then it will be equal to the length of the shortest path. Okay. So this proves the first part. Now for the second part, any thoughts how we apply the same argument for the second part? So that is to show that the predecessor relationship in fact represents such a path. All we do is we just take rho as this path itself. Let me just write it down. So for the second part, take rho as S V, predecessor of V, predecessor of V, etc. Okay. So then follow the same argument. So we get distance V is equal to weight of rho. Okay. If you repeat the same argument, same induction proof argument, okay, so you'll see that at every point here this update happened, so this will hold with equality. Okay, because we have taken that particular path. So how did we define predecessor relationship, right? So if you had defined predecessor of Vi as Vi minus 1, that means, so how did we define that? How did we set that? So we would have set predecessor of Vi as Vi minus 1 only if there was a relaxation when after extracting Vi minus 1 from the priority queue before extracting anything else. Okay, so that means the predecessor relationship would be in accordance with the relax operation, or in other words, all of this will hold with equality. Yeah, so this will hold with equality. So this would have happened. Okay, so in other words, what we would get is from the same, repeating the same argument with this as the path, we would get that distance of V is weight of rho. Okay, from this argument what we already have is, so distance of V is equal to the weight of the shortest path, and with choosing rho as this specific path, what we have is distance of V is equal to weight of rho. So therefore S2 etc 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 pred V.
Student has a doubt, sir. Somebody has raised a hand. Deepali Ande.
Okay, so yeah, please go ahead, Deepali. Yeah, so go ahead, speak.
Sir, I think it was by mistake.
Oh, okay. Okay, no problem. So if anybody else has any question, yeah.
Yeah, so sir, can you describe how did you write this equality here? We get distance of V is equal to distance of rho, weight of rho.
Yeah, so you just go with the argument, right? So if we had taken rho as this particular path, so here, right, this will happen with the equality, because you would have had edge vi minus 1 comma vi as tens. So hence, so the reason it will be, it would have been tens because the predecessor of vi is set as vi minus 1, right? So that would happen only if a relaxation of the edge vi minus 1 vi happened, right? Otherwise there is no other way. So how would you have set this? So the setting of predecessor happens only when you do relax, right? There's no other way out. Only relax does. So relax, just to remind, relax operation is so distance of v is equal to distance of u
like
plus weight uv. Yeah.
why are we
Predecessor
assuming
of,
that there at that particular instance the relaxation is happening?
not assuming it. Otherwise, how do you would have set predecessor of vi as vi minus 1?
No, it's like circular, I think. So, like, is it given that we have set vi minus 1 as the predecessor? The statement says that there is a path between S and V which involves vi and vi minus 1.
Yeah, so but look at the path that we have taken, right? We have taken rho as this path, this specific path. V
Okay.
backward predecessor of V, backward predecessor of V. So
Okay.
Vi minus 1 is the predecessor of Vi, right?
Okay.
So I've taken, so I'm applying the argument for this specific path,
Okay.
right?
You're saying that
So
this is a solution of it.
no, so we are just repeating the same argument with this as the path. So then see what happens,
Okay.
right? So so Vi minus 1 is in this path. So Vi minus 1 is the predecessor of V. So we know that this has happened, right? So the way we have defined the predecessor relationship, so predecessor will be updated only when you apply relax with respect to that edge, right? So you will be, so Vi, sorry, not Vi. So for any edge, say V, predecessor of V will be set to U only if relax UV happened, right? Otherwise there is no way it will happen. Yeah. So do you still see circular argument there?
No, sir.
Yeah, so this that's why we have to take this specific path. That's all. I mean, you just specialize to this path, you go through the same argument, everything will hold with the equality. That is all. Then you know that distance of V is equal to weight of this path. Hence, it has to be minimum weight.
Hello, sir. In the first part of the proof, we showed that distance of V should be less than the weight of rho. So
yeah, for any S to V
yes,
path. Yeah.
It means that the distance of V that the algorithm computes has to be less than the weight of any path that's possible between S and V, right?
Yeah, less or equal to. Yeah, need not be less. Yeah, less or equal to.
So you can just plug in the path, the shortest path that would be there on the right hand side of this, and say that distance of V is equal to the shortest path from there. So
What do you mean by right hand
since
side?
it has to be less than or equal to all the paths between S and V, now I can just take the shortest path in that equation, and the distance that the algorithm computes to V should also be less than or equal to the shortest path. So, and since it's the shortest path, the equality will be satisfied at that point.
See this statement already, right? So this statement that so for any rho, distance of V is less than or equal to weight of rho. This already says that distance of V is the length of a shortest path. Okay, that you already get it immediately, because for any path it's a lower bound, right? So it's at most the distance of V that we have computed in the algorithm is at most length of that path. Okay, now you take this specific path output by the algorithm through predecessor relationship, then we observe that everything holds with the equality. So this is equality here. So all inequalities that we have put will be holding with the equality. So that means distance of V will be equal to weight of the path that we have output through predecessor relationship. So hence, but we already know that distance of V is the length of the shortest path, right? So hence this predecessor relationship, the path represented by that will be equal to length of the shortest path. That is how we are. Okay.
Okay, sir.
Yeah. Okay, good. So that's all about dice cross. So one thing to remember is the complexity of dice cross algorithm. So we'll just take it as m log n, or like I said, if you're happy with the amortized analysis, then you can just take it as n log n plus m. Okay, so yeah. So only thing is the implementation is slightly more complicated than regular heaps. Okay, so and the analysis is amortized. Though I mean it's okay. I mean because we are assuming m and n to be large, so that's no issue. So we'll now discuss the second popular algorithm. So before going to that, so the limitations of dice cross is very well pronounced. So no negative 8 weight edges. So this can be a handicap in many applications. So while assuming that there is no negative weight cycle is kind of fair, but whereas no negative weight edge may not be fair in many applications. There could be applications where it would require that. So people have in fact looked at getting rid of such an assumption. In fact, I think probably even before dice cross, there was an idea by Bellman. Okay, so this is basically an improvisation of Ford's generic algorithm. Okay, so what Bellman thought was instead of relaxing one edge at a time, we relax all of the edges simultaneously. You look at the graph, you relax all of them in one go. Okay, so that is how many edges are there? M edges. So all M edges you relax simultaneously. Okay, but then the question is how many times will you have to repeat it? So is it okay if you do it once, or will you have to do it multiple times? So what Bellman observed is it's enough to repeat it for n minus 1 times. Okay, so the idea is the following. So you have this graph, you look at all possible edges. Okay, you apply relax operation on all of them. So this is my graph. With some edge weights and so on. Okay, 1, 5, 2, 3, 6, 3, 1, 2, whatever. So now what you do is, so you apply relax on each of them. So say this is my start node S. Okay, so initially everybody will have infinity other than the start node. Start node will have 0. Okay, so you apply relax once. So only vertices that will get affected will be immediate out neighbors of S. Okay, but you would have applied relax on all edges. Okay, so then again apply relax on all edges. So then it will be the neighbors of out neighbors of these which already got updated will get updated and so on. Okay, so what Bellman observed is if you do it for n minus 1 times, this is enough. Okay, that's kind of intuitively what happens is it's like progressing like a wave. Okay, so in dice cross we were progressing like a wave, but we are prioritizing. Whoever is the shortest one will be taken first. So okay, so here out neighbor with weight 1 will be taken first, and then possibly either this or depending on its neighbors. Okay, so if this edge weight was 1, then this would have also been a candidate out of the priority queue. So this updation order is dependent on their actual weights. Whereas Bellman's idea was you don't do any of that. You just relax every edge at once, one shot. Okay, so But the idea is, so the shortest paths get updated like a wave. Okay, so all neighbors of S will be get updated with the shortest path in the first wave. Okay, it may not be shortest path, but at least they will have some values. In the second value is second wave, all their neighbors will also get updated. See, there could be a shortest path to this node through some other edge. Okay, so this could be something else, something else, something else coming. This could be shortest path, but at least their values get updated. Okay, but since length of any path is at most n minus 1, there will be only at most n minus 1 edges. So Bellman observed that if you repeat this n minus 1 times, it's more than enough. Okay, so the algorithm is fairly simple. You apply relax for all edges and repeat this n minus 1 times. Okay, I'll formally state the algorithm. So you have the same initialization as before. So distance of S is 0 and predecessor is nil. And for every other vertex, distance is set as infinity and predecessor, of course, is set as nil. Okay, so there is nothing yet. Now, the steps 4 and 5, you repeat n minus 1 times. So what are these 4 and 5? It's basically for every edge, you see if it is tense, then apply relax. If it is tense, apply relax. So apply relaxation on every edge. Okay, so yeah, so now there is an interesting thing that happens. Okay, so if you repeat it n minus 1 times, what Bellman observed was, if there is still a tense edge, then you can for sure say that there is a negative cycle. Okay, so you can detect if there is a negative cycle, while the algorithm will fail if there is a negative cycle. I mean, in the sense that it won't be shortest path or whatever, because you can, I mean, shortest walk or whatever. See, all these algorithms, the shortest path algorithms, they will be basically computing walks. Okay, you cannot really compute a path. Okay, if the graph is acyclic, directed acyclic, only then what you get will be path. Otherwise, it will be a walk. But if there is no negative weight cycle, then walk is useless. I mean, walk will be simply a path. Okay, so only when there is a negative cycle, there is a problem. So that's the reason why all these algorithms fail when there is a negative weight cycle. But good thing about Bellman Ford is you can actually report there is a negative weight cycle if there is still a tense edge after repeating this relax all step n minus 1 times. I'll just demonstrate this with an example. Okay, so this example is taken from Jeff Erickson's book. So only issue there is, I mean, so this is an improvement by Moore. Okay, so that is the implementation that he has shown. But for our purpose, I mean, it really does not matter. Okay, so the improvement. So only thing is, Moore's, see, when you do relax step, so Moore observed that you don't have to apply relax on all of these. Okay, so you don't have to apply relax on all of the edges. You'll only apply relax on things which are likely to have tense edges. Okay, so but let's not worry about that Moore's improvement. Okay, so it improves the bound slightly, but in the worst case, it's the same bound as Bellman's implementation. So yeah, so this example we'll just see. So ignore these things written inside this arrow marks. Okay, so that is with respect to this Moore's improvement. We'll just run Bellman's algorithm. Okay, so S is initialized with the distance as 0. Everybody else will have infinity. Okay, now what are the tense edges? So we'll go through all edges and see if it is tense, apply relax. What are the tense edges here? So tense edges is only those whose endpoint, whose starting point has non-infinity. Everything else will not be tense, right? If both endpoints are having distance as infinity, they will not be tense. Okay, so these three edges are tense. So we'll be applying relax on them. Okay, so if I apply relax on this becomes 3 here. Apply relax on this becomes 10. Apply relax on this becomes 4. Okay. Now you look at again, look for tense edges and apply relax. Okay, so what are the tense edges? So tense edges will be those will be that are going out of these. Okay, that is those whose distance value as per our computation so far is non-infinity. Okay, so all these edges will be tens. 1, 2, 3, 4, 5. So this is not yeah, this will not be tens. 8 plus 4, 12, right? So now we'll be applying relax on these. Okay, so this. So it also depends on order in which you process. So if you process in yeah, so no, okay, so this is fine. So order, I mean, if you process in this order, so if you choose this edge first, this will cause relax first, and then again this will be relaxed further. This, okay. So if you choose this edge first, then this will not be a tense edge at all at that time. Okay. But anyway, it does not matter. So we'll just imagine that at one point you see all possible tense edges and apply. Okay. So after the second iteration, the situation will be this. So these are the updates, and these will be the edges that will be in the predecessor relationship based on the relaxed steps. In the next step, this will be tense. So is there any other edge that will be tense? Okay, so there is no other edge that will be tense. So this is the relaxed step. Okay, so since this is a -5, so this naturally will be tense. So this edge is tense again. Okay, so then the relax will happen. Now, oh, okay, so this edge was also tense here. Yeah, sorry, this is also -3, right? Yeah, this edge was also tense here. So the relax also happened to this. So these two were relaxed here. Okay, so predecessor was updated accordingly. And then again, one would find that this is also tense. So this is the update. So after this, is there any tense edge? You can see that there is no tense edge. Okay, so this will be our shortest path tree. In fact, fairly simple looking tree here. Okay, so only difference here is you will be relaxing. You're looking for tense edges for all edges. So it's like look at all edges at once, apply relaxation. But the only thing is, yeah. Somebody wanted to ask a question. Somebody turned on the mic.
How do we get 4 in F node?
No, sorry. Where?
That F node carries a value 4 after relaxing in stage 3.
Let's see. Yeah, this I think it should be 5, right? If you relax this, yeah, it should be 5. Yeah, thank you. Because this was wait. No. This was okay.
Is it 9 minus 5?
Yeah, it was 9 minus because it was updated, right? You're right.
Okay. Yeah, got it. Thank you.
Yeah, because this became so. See, that again depends on the order. Okay, so if you had processed tense edge incoming to this, right? So see, we don't really say in which order you process these edges. Okay, for every edge you do it. So it could have been 5, but at the next iteration it will become 4 any case. Okay, so yeah, so in this implementation, so the edges, incoming edges of this vertex B have been processed, so it became 9. So after that you will process this edge, this tense edge, so then it will become 4. Okay, otherwise it could have been 5, and this iteration it will become 4.
Sure, thank you.
So see these vertex labels here, this is basically an improvement. So what Moore observed that you don't have to apply check for tense edges for all edges. What you do is you only look at likely candidates. So all outgoing edges of this vertex needs to be checked first up. That is why it said S here. Okay, so then only outgoing vertices of these 3 needs to be checked. This is ABC here. Okay, only outgoing vertices of D and F need to be checked. That is why DF here and so on. Okay, so Yeah, so but it's slightly non-trivial to see the improvement, but in the end, the improvement also does not matter much. I mean, in the sense that overall the complexity will be similar. Okay, so that way it's not. So yeah, the book basically shows with respect to that improvement. That is why this ordering is seen. Okay, so yeah, but it's not much different from the regular Bellman fold, except that all of this you won't even touch. That's all. In principle, you need to do. You need to look at all of this. But if you see, the moment you see the endpoints are both having distance value infinity, you don't even have to apply or check for if it is tens or not. Okay. Okay. So we are going to argue the correctness. Can somebody remind me of the time? Okay, we have time, right? Okay, good. So the idea is, like I said, after the ith iteration, what we expect is all vertices whose shortest path from S will use at most I edges, they would have got their distance. Okay. So that's essentially what we are going to do. We'll bring in notation for that. So let's say D with subscript less than or equal to I, V with the length of a shortest walk. Okay, so we'll just write, so here it need not be a path, shortest walk from S to V that contains at most I edges. Okay. Now, if there is no negative cycle, then D less than or equal to NV would be the length of a shortest S to V path. Okay. If there are negative cycles, you might be taking that negative cycle and all. What you will be getting will be walks. Okay. So if there is no negative cycle, then D less than or equal to NV will be the length of a shortest path. Okay. And of course, when we take I as 0, distance from S with using at most 0 edges will be 0. And for all other, you cannot really reach from S without using any edge. So we'll set it as infinity. Okay. That is, yeah, it's not reachable, indicating that it's not reachable. So this kind of is the formalization of the intuition that we have. I mean, that I had mentioned about the algorithm. So the algorithm basically works like a wave. Okay. So neighbors of length distance 1 will be updated. When I say distance 1, the number of edges 1. Neighbors of distance 2 will be updated, and so on. So what is guaranteed is after ith iteration, say for this node, if the shortest path from S to this node uses at most I edges, okay, so then this vertex should have the correct value of distance after that iteration. That's exactly what we are going to argue. Okay, so that basically justifies the number of iterations being n minus 1, because any path, any simple path will use at most n minus 1 edges. It won't use more than n minus 1 edges. Okay. So this is a statement that we are going to prove for the first part of the algorithm. Second part, I will not be really discussing it. Why negative weight cycle? I'll leave it as an exercise for you to prove. So yeah, the statement is after I iterations of Bellman fold, for each vertex, distance value computed by the algorithm is at most length of a shortest path that uses at most I edges from S to V. Okay, so this is length of a shortest path.
Hello.
Yeah.
Sir, in the definition, D less than or equal to n of V is the length of shortest S to V
Walk.
path or walk only, right? Okay.
That's what I had written there, right? So yeah, so this walk is missing here. Yeah, it will be a walk. Okay. I mean, if there is no negative weight cycle, it will be a path, in fact. But in general, it will be a walk. Walk from S to V. Okay. So this is what we are going to prove now. Okay. So if you prove this theorem, we are done with the correctness about the distance computation. Okay, so yeah, the negative weight cycle we'll leave it. Okay, I'll just give you intuition why it is, but yeah, it's not very difficult using this theorem itself. Okay, okay. So we'll be proving this by induction on I. So base case will be I equal to 0. So we'll look at an induction step. Okay. So so let's consider an arbitrary vertex V and rho be a shortest S2V walk of length at most I. Okay. So that weight of rho is at most the distance or d less or equal to IV. Okay. So now by induction hypothesis, we would have assumed that okay, if you look at walks of length at most I minus 1, the distance value would be shortest weight of, so or distance of any node u will be the shortest weight of such walks that uses at most I minus 1 edges. Okay, but let's be more specific what we really want. So let's consider the last edge of rho. Okay, it's not w, rho. So maybe I should have a picture. Let's consider rho. Yes. Blah blah blah. We end at v. Okay. So the number of edges is I edges. Okay. So let's look at the last edge in this walk, which is u. They might revisit vertices and so on. Now, so what we want to argue is, yeah.
Excuse me, sir. Sorry for interrupting. Can we go to the last slide?
Last slide. Okay.
Here we told that let rho be a shortest walk from S to V of length at most I.
Yeah, with
Here
the
you mean that
so many edges,
edges, right?
Yeah, edges,
Oh,
edges.
okay.
Yeah, sorry. I mean, I've been using length also for weight. Okay, sometimes, but I hope I have corrected it whenever I did that. Yeah. Okay, so let's just look at this picture. So at most I edges. So rho is shortest weight among all this. Shortest weight among all such. Okay. Now let's look at this S to U. So what can you say about this S to U segment of this rho? Is a shortest S to U walk of length, by length I mean edges, at most I minus 1, right? So by the optimality of shortest walks or shortest paths, right? So if rho is an S2V path which uses at most I edges, that is length I, and shortest among all such, then if I chop this at the predecessor of V along this path, this will be shortest S to U walk of length I minus 1, or of among all those which uses I minus 1 edges, right? So we want to prove that. So want distance V is less than or equal to D less than or equal to I V after I iterations. Now what we have by induction hypothesis is distance u is less than or equal to di minus 1 of u, okay? But since this row chopped at u is also such a path, okay? So weight of row minus, sorry, weight of uv is equal to distance u, okay, which is less than or equal to di minus 1 u, sorry. Yeah,
Hello?
so this is what we have. Yeah.
Sir, the statement S to V is the shortest, like the above one is a shortest S to V, S to U walk of length at most I minus 1. This is, how did we write this directly?
So this is from the optimality principle of shortest walks, right? Or shortest paths.
Okay, and then by induction hypothesis, we are saying that since this S to U is like I minus 1, so this holds.
It uses at most I minus 1 edges, so this statement holds. Statement that we want to prove is it holds.
Okay, okay.
Then we just relate to the weight of the chopped path with the weight of the whole path, which is nothing but, so so distance of u is nothing but weight of row minus weight of this edge, right? That's what we are going to use. Okay, so is it clear to everyone? So I have everything written, the same thing written here itself. So we'll just see. Okay, so yeah, so I hope that picture helped. So now, so uv is the last edge of row. Then by induction hypothesis, distance of u is at most distance less than or equal to I minus 1 u after I minus 1 iterations of Bellman Ford. Okay, so that qualification is required after I minus 1 iterations. So now let's just start at the ith iteration. Okay, so at the ith iteration, so there are two possibilities. Either distance of v is smaller than distance of u plus weight of uv, or it is not. Okay, so if this is the case, then distance v is updated to distance u plus weight of uv. Okay, oh sorry, either this is small. If it is not, it will be updated. Yeah, if it is not small, it will be updated. The edge will be tense. So if it is small, the edge will not be tense. So I'm sorry. Okay, sorry for the confusion. So at the ith iteration, either this happens or it is getting updated. In either case, what we have is distance of v is at most distance of u plus weight of uv. Now by induction hypothesis, this is at most di minus 1 u. This is what we have. Plus weight of uv. So this is nothing but d less than or equal to I. This is nothing but the weight of rho. Okay, so this is nothing but weight of rho, which is equal to d less than or equal to I. Sorry. That is all. So all we did is, so let's go back to that picture once again. So we took a shortest walk from S to V that uses at most I edges, or exactly I edges, let's say. And by induction, so what we have is up to U. So for U, the condition satisfied, that is distance of U after I minus 1 iterations is at most D less than or equal to I minus 1 of U. Okay. So now using this, we just look at the iteration, ith iteration. At ith iteration, either this edge might have caused a relax or it may not have. Okay. So in either case, what we have is distance of V is at most distance of U plus weight of this edge. But we know that distance of U is at most this value, di minus 1 U. Okay, or d less than or equal to I minus 1 U. So hence, now if I add this, what I get is, so weight of uv plus d I minus less than or equal to I minus 1 u is nothing but d less than or equal to I of v. Okay, So in other words, distance of u will be distance of v will be at most d less than or equal to I minus 1 of v. Okay, so we'll just go back and see. This is what basically completes the argument.
Hello.
Yeah.
Yeah. So just a small question, sir. This
Yeah.
d of p less than or equal to I from di minus 1 u plus weight of uv. This followed from rho, right? Because
Yeah,
we
we followed
assumed
from
that
rho is
uv
the
is the
shortest.
last
Yes.
edge.
Yes.
Okay.
UV is the
Okay.
last edge, and we assume that rho is the shortest. So that
Okay.
is important. Okay, so this is important. Shortest walk is important. Yeah.
Okay. Okay.
Yeah. Otherwise, this equality of di minus 1 u would not have had. Okay, so that is a problem. So if you take an arbitrary path rho or arbitrary walk rho, this won't work. So you need shortest walk. Okay. Okay, so quickly a word about detection of negative weight cycle. See, so what this gives is, so if the graph had no negative weight cycle, so any shortest path will use at most n minus 1 edges, right? So by this argument, I mean this theorem, so what we have is at the end of the algorithm, I'll go, distance of v is less than or equal to d less than or equal to nv. Okay. So now when is this the shortest, the length of a shortest S to V path? Only when graph has no negative cycle. Okay. So this is equal to length of shortest S to V path only if G has no negative cycle. Okay. So yeah, so that's pretty much it. So this becomes, so what the value that we got is a weight of a shortest path or length, weight of a shortest path, not length, weight. Shortest path only if G, in fact, if and only if G has no negative weight cycle. Okay. So then, so why our last step of the algorithm is correct? So if G had no negative weight cycle, for every vertex V, distance V would be the actual weight of a shortest S to V path, right? So once we have everything, distance V representing weight of a shortest path, there will be no tensed edge at all. But if there is still a tensed edge, that means there has to be negative cycle. Okay, so that is a kind of intuitive reasoning. I mean, this is also almost formal reasoning, but I'm not writing it down. Okay, I just want you all to think about it and write a formal argument. But the formal argument essentially comes from here. Okay, so these two observations. So one is here, which I didn't write, that there should not be any negative weight cycle. So this holds only when there is no negative weight cycle. So you combine this with this theorem when I equal to n. So in fact, what we have is, so in fact, I equal to n minus 1. Okay, so you don't even need n, because any path, a simple path can have at most n minus 1 edges, not more than that. So yeah, so combine that with this. So you'll see that at the end of n minus 1th iteration, all vertices should have distance value, which is length of shortest path. Okay. If that is not the case, the only possibility is there is a negative weight cycle. Okay. So yeah.
Hello.
Yeah.
Sir, at last we have said that it is less than or equal to, but we know that it should be equal to.
Yeah, that will be equal to, yes, of course. It will.
So, like, how
Yeah.
do you argue for that?
See, the point is this statement does not really assume no negative weight cycle, right? So that's the reason why the less than or equal to holds.
Okay.
That is all. Yeah.
Okay.
So when you assume that there is no negative weight cycle, then this will be equal to, yeah, this will become equal to. And the corresponding walks will also be paths.
Sir, even if there are negative weight cycles, since we are restricting to n-1 edges, the right-hand side part would remain fixed. Won't it be?
Right hand side is kind of fixed, yes.
Left-hand side will be going on decreasing.
Yeah.
So that's why the negative, this less than or equal to is holding. You are saying that only, right?
Yeah, I know. I think you're probably right. I mean, this might even be equal to. Okay, so you can probably even prove that it is equal to. See, yeah. So, because
But
if
since
you
we
take
did not
the
assume
short, yeah,
anything
this will
about
be
negative
actually
weight
equal.
cycles.
No, even without a negative weight cycle, I think this will hold with equality is what I believe. So because for the proof, right? Where is that? Sorry, is that picture? Yeah. So if you assume this is equal, right? Then I will have equality for V as well, right? Yeah. So you can actually prove equality as well, not less than or equal to.
Because in the base case also it is equal, and in the induction hypothesis also it is equal.
Yes. Yeah. You can prove. I mean, even it doesn't matter if it is negative, if there is negative cycle, because we are talking about length of, I mean, walk of length I-1 or walk that uses at most I-1 edges, right? Srinivasa, can you stop the recording?
Sure, sir.
Yeah. So, sorry. Yeah. So this will, I mean, I think you can actually prove the equality. I don't see any
But